Hi, folks. Welcome to the Break Key. My name's Henry, and today we're going to go back to the Forth ROM and we're going to start investigating variables and storage space and putting stuff into the heap. Although the way I've been looking at this, the heap really isn't applicable because we're not doing anything that's doing protected memory or anything like that, other than just making sure that we're not having a parameter stack collision. But even, yeah, we'll figure that out. So, Forth is a postfix language. That is to say, you put your parameters onto a stack, and then your word operates on the parameters that are on that stack. You've seen this before. If you think in RPN like I do, this makes perfect sense, and it is perfectly sensible, and everything is just hunky-dory. However, in the Forth standard, there is a very significant key element that is not postfix. And it's going to drive me bat crap insane. So follow along as we try to figure out how in the world to get a postfix language to do prefix stuff. Things are going to get a little bit brain melty, not only because I'm dealing with prefix notation and a postfix language, but I'm also dealing with multiple stacks, and I'm also dealing with different different concepts. And so the multiple stacks we don't have to deal with just yet, but there are three of them according to the standard. We have the control flow stack, the data stack, and the return stack. These three right here. So that's not too difficult. Right now, all we're really worried about is the data stack. That's it. As we get into compiling and we get into conditionals and things of that nature, we'll be looking at the control flow stack. And when we get into subroutines and things, we'll be looking at the return stack. And of course, it's pretty standard. You put the stack ID and then the before dash after. That's something that we've been seeing before, but we're going to see more of as we move forward, and it's going to get a little more confusing because there's also parse text notation. What we're looking at here are words that are going to actually parse text. And here we'll see like the stack it's going to be using, whether it's the data stack or what have you. And for parse text words, the data stack may be in use, and then we'll have whatever it's going to consume on the stack. And then in quotes is going to be the parse text that we're going to be looking for, followed by that. And there will be abbreviations as we see in here. So let's start with the first little brain melter. Create. And this is kind of a fundamental one because create's job is to put a word into the dictionary. And that's all it's done. And as you can see, we have parsed text notation. And what does that mean? That means that it's going to be looking at text in the token stream after the word itself. And then we have another concept that we haven't looked at. And now, given we've looked at the stack pointer, but we haven't looked at what data space is. So data space should be relatively simple. And just looking at the logistics of what I need as far as data space goes, I need a place where I can store the store the words, their definitions. And in the case of variables and other items that store data in the heap, I need a place where they can go ahead and access those relatively reasonably. Now, in the standard, it talks about contiguous regions in the data space, where create establishes the beginning of a contiguous region of data space, whose starting address is returned by the created definition. Okay, easy enough. That's part of the definition of create. This region is terminated by compiling the next definition. Well, what the heck does that mean? Well, effectively, for what we're putting together today, that means, we terminate a contiguous region with some other words. And there are other words which we'll be looking at that allow us to increase the space allotted to this variable and, or to this word. So right now, the simplest thing to do is going to be to just say, all right, data space starts here. And if we go back to what we've been doing with the memory map, it's a little bit all over the place. I haven't consolidated it, but you've got the system stack, which starts at 0, 100, and as you know, the stack with stack pointers, the value of the stack pointer decrements. So we've got a full 256 bytes or 128 cells of stack space available to us for the system use. Now at 100 at that location is where we start with our error vector table. At 200 hex is where we start with our system variables, giving each of those a full 256 bytes worth of space. This could potentially be compressed later. Now, our screen space has to be aligned at 200 hex or at 512 byte increments. So I can't start screen at 0, 300 like I tried to do some time ago. I can only start it at 0, 400 or at multiples of hex 200. So we're starting that at 400, which means that I've got an extra 256 bytes worth of space to play with, or 128 cells. I could, if I wanted to, consolidate things and move the parameter stack or the data stack into that space, but I'm a little bit concerned about that not leaving us enough room to do what we want to do. I don't want collisions to happen. I'll deal with the movement of things later. If nothing else, I can move the system variables onto the 0 page. I can move the screen into the 200 area, and I can give myself a little more stack space above the screen memory, and we can consolidate that way. Well, now the other thing that we've got with the screen space is that is the top of screen space or the bottom of the screen, but we routinely go beyond that in dealing with scrolling and things of that nature. So, all right. That means that it's not safe for me to put data at 0600. Something's going to be written there when we're writing to the screen. It should be safe for me to allow myself as little as one line or hex 20 or 32 bytes at the end of it. So what I can do is I can say that my data space, we can start that at 0620. Ultimately, this may be changing, and it may change based on the memory configuration of the machine that this is running on. Right now, again, my target is a 64K machine, or as this is being written, a 32K machine, so that I have all the way up to hex 8000 available to me, or I should say hex 7FFF. All right, so we'll start it there. That's where our data location is going to begin. In our boot code, where we're setting up our initial variables, set the VGG autoclave screen. Okay, that's the main loop. Where am I setting? Okay, so that's simple enough. Now, there's another word that we're going to want to put in here that the standard defines, and that's called here. And the purpose of here is it gives us the current data space pointer. Now, here does nothing more than put the current location of the data pointer on the stack. So, okay, so that's very simple. Good. That's simple enough. And then there are a couple of other things that we're going to be using. And these are going to be our, let's see, what does the Forth standard call them? I know that one of them is store, which should be the exclamation point. Let's see what it calls that one. Yep, store, which is the exclamation point. And the other one, I believe, is just simply called at. Yep, at. Okay, great. So it grabs a value. This is, again, these are very simple to implement. Okay, let's go ahead and see if it assembles, which it does. That's wonderful. Oh, well, that didn't work. I did something silly and obvious. I'm sure I did. Oh, okay, I see. Yeah, stupid me. It's supposed to be an FDB, not an CB. So that's going to be FDB store. Good. DB here. Okay. That's a simple error to make that only putting one byte in instead of two. That'll definitely screw things up, won't it? Let's do a make assemble again, and that works. That looks good. Let's do a make run. Okay. It's F5. And I don't know what that means. That's an FCV. Okay. Now I get it. Good. 8447. Here's telling me 8447. What's going on with that? Let's see. Load A. Ah. Yes. It helps if I'm using an address to use a 16-bit wide register when moving things around. Don't you think? All right. All right. We'll try that again. Move you over here. Let's set 5 that. 1568. 620. And that is correct. Absolutely wonderful. So now what I want to do is grab this over here and come over to 620. So if I'm doing this correctly, I should be able to do here. I should be able to actually know it's a value, then the location, then. And if I want to put, let's see, I'm still in base 16, so I can do this. I want to put a 4F here, and I want to store that. And look at what we found over here. Lovely. That's perfect. And then if I take here and let's look at dots dot, there's nothing there. So if I do this is where things are going to get interesting, because if I do this correctly, if I do 620, which is the here, okay, and then Oh, that's right. There we go. It likes it. Bang. Nice. Lovely, lovely, lovely. All right, so we've got that working. Now, if I do something, because here's what I'm looking at. I'm looking at this bit right here. I should be able to play fast and loose, and this is where it's going to come and bite me in the butt later. This is what we call foreshadowing, because what I haven't done is I haven't put anything in there to programmatically protect areas that we shouldn't be playing with. So, keep on moving because that was a user-initiated break. If I do a 621 and recall that and look at it, I get a 4FFF, which is exactly what I'm looking for. Now, where the heck did I store? So if I do 232 OA 232 store, and then I do a here dot, it's not happy. Oh, I see why that went awry. That makes sense now, because what I tried to do is I tried to store. Got it. Okay. So that's going to cause me all sorts of problems because I'm trying to change a byte value in a non-byte location. So I'm going to have to fix that. Now, here's the thing. I'm looking forward to when I have to make this like consistent with the Forth standard, which is to say that the radix is simply a variable that it uses. So it doesn't actually do it the way that we're doing it here. I think I mentioned this before. So I am going to worry about that later. I'm going to worry about that later. Because that's something that's going to jack up some other things, and it's not cognizant to what we're doing right now. It's something that's a later thing, but it also shows that if you go outside, because we don't have the protections in here, we can jack up the system by putting values somewhere where we're not supposed to be playing. Okay, so with that said, the system variable area does have byte-wise things, and if I use this to do it, it's going to be using word-wise or cell-wise things, which is 16 bits, and it'll drive everything crazy. But with that said, we do have working store. So if I put like in a safe variable area, let's see, let's put a couple of values on the stack. Let's put 20 on the stack, and let's put 20 on the stack. Okay, 30, 20. Those are on the stack. Now, here's the trick. The current top of stack I know to be at, that's going to be 7FFE and 7FFE. So what I should have is, let's see, 7FFE, let's put a 40, 7FFE, and bang that in. That works. And so if I do a dot dot, I should see a 20 and a 40, or I see a 14 and a 40. Okay, beautiful. Because this was done in decimal, this is in hex. So what that tells me is we have a working storage facility. All this, as far as these words here, fetch, store, and here, those words work. We've got a working data storage capability, but here's where things get interesting. The next thing that I need to do is be able to advance the data pointer. This, again, should be easy. Now, over here, we have cells, N1, N2. N2 is the size and address units of N1 cells. So that's very simple because our cell size is 2 bytes. Okay. And if I do cell plus, add the size and address units of a cell to address 1 giving address 2. I am going to implement, we'll go ahead and implement the cells, those two, real quick, just to make the math a little bit easier. Real sweet, got it. All right, and one. Beautiful. Give me 10, beautiful. All right. Something went awry. That usually means that I did something stupid that's real easy to fix. Cell P, FCB cells. Oh, because I put C instead of D. How many times am I going to make that mistake? Ding! All right. Save. Whoop. Save that out. Run it again. And that's going to be here, do dot. Great. And then let's do this. 16. It's at 620. Interesting. Great. All right. Beautiful. That works. We've got those two working. That's great. Now, with all that, we've got the framework to be able to handle just about everything. But there's one more thing that I need to do, and that is to actually allot space. And so when last we looked at it, we were seeing that, we had to allocate contiguous, blah, blah, blah. Okay. But we were also introduced to a little word called allot. And we haven't looked at allot yet. So we're going to look at that now. If n is greater than 0, reserve n address units of data space. If n is less than 0, release n address units of data space. If n is 0, leave the data space pointer unchanged. So here's the fun fact. When we go back to here we go. When we go back to the contiguous region idea, if we do a create, then the contiguous region is terminated by compiling the next definition. So a system guarantees that the region of data space allocated using allot shall be contiguous. Okay, so a lot shall be contiguous with the last region allocated with one of the above words unless the restrictions of the following paragraphs apply. Which basically means that what I can do to cheat this and to make it happen quick and easy is allot will simply take the number of, now allot is using allot. So let me make sure that that is bytes. No, address units of space. Address units of data space. Right. And that is not cells of data space. Data space pointer is aligned and n is multiple of the size will remain. Okay. Data space pointer is a character line and is a multiple of the size of a character. When allot begins execution, it will remain character lined. Okay, a multiple of the size of a character. If the data space pointer is aligned and n is the multiple size of a cell, it will remain aligned with allot Fisher's execution. All right, so all I'm going to do there, I'm not going to deal with this complexity of character versus cell or anything like that. Everything's going to be, 16 bits. We're just dealing with everything being 16 bits. So allot will be simple. We're automatically aligning everything to we're automatically aligning everything to 16 bits, but we're not going to worry about it because the alignment doesn't matter because we're dealing with, okay, never mind, shut up. Alignment doesn't matter in this implementation. Alignment does not matter. It makes no difference because we've only got an 8-bit data bus. So in this case, align, and we're going to do an FDB, cell P, We're going to F5, and let me make sure that I can actually. So what I should be able to do is to allot here dot 1570. Perfect. Perfect, perfect, perfect. Except for the fact that something went awry over here because this isn't supposed to be happening. Oh, I did an RTS, that's why. I've got that scrolling issue that came back again. I'm going to have to fix that. I'll leave that for another time, and I'll actually fix that off camera. I'm not sure what's going on, but we'll worry about that later. I thought I had that fixed, but oh well. So let me try this again. 1570. 1572, which is exactly what's supposed to be happening. So now, with this all done, what I can do is start looking at how I'm going to look at the up and coming token stream. So that's going to be a dive into what was going on with parameter processing. But while we're sitting here and waiting for that, and I'm ramping my brain to go into that realm and going to take a break to do it, let's do a little montage of refactoring our let's see if there's anything on the stack code. Looks like we're fine. Now it's time to take a break before I attack the token stream. When last we left our heroes, I do believe we had pretty much taken care of, like, just the allots and everything like that, just dealing with what we call the data pointer. So now comes the fun part. Now comes the part where we have to look at what's coming ahead. And I'm going to look at hang on just a second. Let me look back at my notes. Yes, I'm going to look at create. Yes. That's the one that I believe I was ranting about back at the beginning of all this. All right, so for create, we have the space delineation with the name. It skips any leading space delimiters, parse name, which is delimited by a space. Now, we're looking at the token stream. So let me, that's better. So now we can see what's going on. So the token stream. So I just put in a word here like, say, depth, and then put a dot after it. It's going to say 0. Okay, that's fine. What's the token screen? If I look at this line, what's happening is the first thing is the space tells the token parser that we're ending a token and we're going to start doing a search for the word. Then everything after that is going to be another token. In the case of create, what we're actually having to do is look at that space will tell it it's done with create, it's going to go on. We have to look at everything after that space. We have to hand that over to create itself so that it can go ahead and process what's coming up next. It's going to ignore the preceding spaces, and then it'll say, all right, I've got FOO. And in the case of create, space again delimits, and at which point it says I'm done with token processing, and I need to kick that right back over to the regular token processor. With that said, let's take a review here, because quite frankly, I forgot how it works, of what the token processor itself is doing. Let's see. Expects a numeric digit. The first thing we're doing is we're going to Proclin. which is processing line for tokens, cobbers, DX, and Y. Okay, yada, yada, yada. All right. Now, my question is, what variables do I need to pay attention to when I start working with create? Counter blank, have we hit the cursor location?
Eventually.
Negative A, yes. Okay, that should be where I'm at. So, with that being the case, that our token pointer position is at A, S, that's the value that I want to retrieve. That's the value that I'm going to play with. When that's restored and we pop back up, the next thing that's going to look at that is going to be our token processor. So, if I'm playing my cards right, I should be able to just skip a token. Or I should be able to just grab that token. Now, create does not need to check the stack for anything else. But what it does need to check check for is to see if there's anything on the token still in the token process. So what we'll do, we'll grab that position from X. So what I need to do is LEAX. Okay, something important to note. You will notice that when I put this together, I am not checking to see if we already have a word defined. This is purposeful because Forth allows you to shadow old words. If you get the link field, and if you get the location of the word, like find out where its code field address is, then you can hold on to that and shadow over the word and then use the old word by doing whatever the heck. Okay. Yeah. But that's going to sound a little bit rambly, but Forth, you can shadow things. We're not checking to make sure that it's already there because that's on purpose. Okay. Okay. So that should take care of that right off the rip, I hope. And if that worked, if that is, and it will be surprising if it is without error, this should, like, actually put stuff on the stack. I am going to step through this first to make sure that I haven't done anything stupid. Okay. That's why that didn't look right. Okay. So in this case, we're going to... Hey, Kathy, how's it going? So my mom was a systems engineer for Tandy Radio Shack, for Tandy Radio Shack Company through the mid 80s and into the early 90s until basically the computer centers and the position of systems engineer stopped being a thing, at least in the state of West Virginia. But as a result of that, we were a Tandy family, and Mom had kind of a little special place in her heart for the Coco as well, because that was the first computer that she used to help her transition over to the new career of computer engineering and computer science. And guess what? Tomorrow is her birthday, and she's going to be her 80th birthday. So I was wondering if y'all out there in the community, in the Coco community, and in the Tandy community at large, could do me a favor and wish her a happy 80th birthday. And here's how you can do it: go over to Mom's YouTube channel, Faith Gernhardt. Grab one of her videos and just give her a happy birthday on one of her videos. And yeah, you can go ahead and tell her that the Coco community or the Tandy community or, wherever said happy birthday. Happy 80th, Mom. Did I fix that? Oh, yeah, I was in the middle of fixing this. Did I forget to RTS? Because that's exactly what that looks like. That looks like I forgot to RTX. RTS. Return from subroutine. It helps to remember these things. Now, everything else looked like it was going fine. I'm going to try this, and I might regret it, but I'm just going to try sending it and seeing what happens. And if things have gone according to plan, there are a few things that I should see. Create. Whoop, nope, let's try just F5, F5, F5. Create foo. It's an okay. Let me check what's going on in memory here. So that is that. And let me pull a deke window over here real quick and point you at, we're going to just see, 1, 2, 3. Okay, so you can see 3. This is 1, 2, 3. So that's going to be there. That's going to be 21, 22, 23, 24, 25, 26. 0626. Load D062D. 062, okay, 062D contains 8, 9, A, B, C, D. That's correct. Push UD. What the heck is that? Oh, okay. Let's try store B, comma X plus. And then that actually was supposed to be a 5. We'll save that out. And we'll give that a full send. Run that. That's okay. Let's look at what's going on in memory. And let's go at what's going on in the deke window. Where's my deke window? There's my deke window. Yep. Okay, that actually looks correct. So let's do a depth dot. There shouldn't be anything on the stack. And if I run foo, it worked! Yes! It worked! Yes! All right, and so if I do this, foo, and we'll go ahead and go with like 37, store. I said store, which is actually that key. There we go. Looking at memory again, so I should see that show up and not clobber it. I should see it show up right here. Actually, since that's going to be a 2-byte value, I'll go with that didn't work. It did. It did. It worked. It worked. Yes, 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 yes. Now, the other thing that did not happen is we need to, in order for that to truly be a variable, we need to do this. Okay. What just happened? Oh, it's not alloc, it's a lot. I forgot about that. C, D, E. Okay, this makes me happy. Now, what this means is our next word. Okay, verify the word is actually being stored properly, which is good. Verify the word actually works. We've done that. Is we now have one more word to define that takes care of variables and variable storage. And it actually riffs off of create and allot. So here's what this looks like. If I do a create, we got 64A, so that's going to be the next place we go. This right here, create bar 1 cells allot, is a synonym for variable bar. So that means that this should be, famous last words, should be easy to implement. Let's do that. and that's taken care of. Now, a fun little fact about this. This is exactly what something like this is exactly what our compiled code, a lot of our compiled code, is going to look like when we actually start being able to define words that do things. That's what we're looking at with that. And the fun part about that is we're going to be doing token processing in a compile mode. So compile mode is going to have, that's going to be fun. I'll deal with compile mode later. Let's test this real quick because there is one other thing that I want to do. I got to set a breakpoint here. Oh, this is one of those days where I'm glad I'm not monetized because I might be demonetized as a result of it. Okay. And it worked. Store. Oh, no wonder you don't know what that means. Because I'm in, right. Nice. All right. All right. Lovely. Absolutely lovely. And now, for my next trick, we've got, we've got the create, we've got the, a lot, we've got all this stuff. We're putting variables in memory, and that's wonderful. But there's one other thing that Forth has that I don't want to forget about and I don't want to do off camera, and that is a constant. Now, the difference between a constant and a variable is that a variable, as you can see over here, we've got this, what it's doing is it's putting this address, 6289ABC, 62C, onto the stack when we do that, and then, what a constant will do is it will put the actual value onto the stack, okay? So what we'll wind up doing is instead of placing this 062C in there, everything's going to stay the same, except we're actually going to put the value in that location instead of a memory location. So let's go ahead. Let's get this going. This is what I get for forgetting to put in RTSs. Oh my goodness. All right, everything else was working. So I'm just going to send it. Face, no. 16 base, face, constant. Foo. Okay, what have I got here? Da 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 da. Okay, great. So if I do a foo dot, bang, a flippin' rang. We've got constants, we've got variables, we've got an arbitrary word which points to a location in data space. We've got the capability to take that allotment and make it much bigger if we want to. I call that a success, and now it's time for the outro. As you can tell from the excitement that you just saw a moment ago, we do have a bunch of new working words. We have variables, we have constants, we have the ability to make an array. Here's the beautiful thing about it is like now if I just do like an allot right after a create or even a lot right after a variable, I got this nice big space that I can use for arrays or anything like that. And we've got all the other math that we can use to make that do those calculations. And since we know that our cell size is 2 bytes, you know, pointer arithmetic should be ridiculously simple when we're dealing with arrays and things of that nature. So with all that, I'm calling this a rousing success. I want to say thank you so very much for coming in here with me right here at the break key. Y'all have a great day. Like, share, subscribe. If you want to see some of the merch that I've got available, just go ahead and go to the site that's in the description down below. Thank you so much and have a wonderful day.